Hello, welcome to the e-learning on the topic Hall effect. Hall effect is used to find out the type of charge carriers in a semiconductor. Let us consider a sample, semiconductor sample with a thickness T. And if this sample is applied with an electrical field in the positive x direction, let us consider this field as Ex. Electrons will be moving from, for example, this is an n-type semiconductor. This is a semiconductor which is doped with impurities. For example, n-type impurities, like in the case of silicon, if it is n-type, that is phosphorus doped silicon, phosphorus doped in silicon. Let us consider a semiconductor doped with impurities to make it n-type. If it is doped with phosphorus pentavalent impurities in silicon, for example, a silicon is an intrinsic semiconductor, and if it is doped with a phosphorus, then it becomes a n-type. We have to find out, let us consider this is a silicon sample doped with n-type phosphorus material, that is the phosphorus pentavalent material, which make it as electron rich, electrons as majority carriers, make the silicon material as an extrinsic semiconductor. Normal silicon, undoped silicon is an intrinsic semiconductor. If you dope with impurity, pentavalent impurity, it becomes an n-type, and if we dope with a trivalent impurity, it becomes a p-type. So this semiconductor, if we have to find out in this sample, in the silicon sample, the type of charge carriers, we have to confirm whether the electrons are the majority carriers and the number of charge carriers, how many charge carriers are there, and mobility of the charge carriers. So all these things we can find out using Hall effect. So what we have to do is, we have given an external field and we apply a magnetic field perpendicular to the direction of the flow of electrons. Let us consider this is the flow of electrons from one end to other end, and we apply a magnetic field perpendicular to the flow. When the magnetic field is applied perpendicularly, the electrons will be shifted, their path will be bent, and the electrons will be accumulated at one end of the sample. Electrons will be accumulated at one end of the sample, and there will be a deficient, that is electron deficient condition occurring at this particular end of the sample. So electron rich, electron deficient. So what happens is, if you measure a potential, there is a difference. If you measure a voltage across the breadth of the sample, consider this is the breadth of the sample, then we measure a voltage that is called as Hall voltage. So the creation of a voltage perpendicular to the flow of electrons and to the applied magnetic field is called as Hall effect. And using this setup, we can find out the Hall coefficient or Hall constant, which determines the n-type or p-type charge carriers, and Hall mobility, which determines the mobility of electrons and holes. So what happens is because of the force by the magnetic field on the electrons will be going on accumulated at one end, and therefore there will be more and more electrons will be created at one end. So what happens is this will become very negative region, and this will again repel the electrons which are forthcoming towards this particular region. So there will be an equilibrium by the force because of the Hall field. Let us consider the Hall field as Ey. So we can write an expression as Ey on the electron is equal to the force because of the magnetic field. Let us consider this is the magnetic field Bz, or can Hz. For example, you can mention as Hz, for example Hz into the charge into Vx. So electrons are having velocity Vx moving in the positive x direction, subjected by the magnetic field. So now we have electrons, we have the charge on both sides, we can be cancelled. The current current in the sample can be given as the carrier concentration into the charge Ne, the area of cross section, and the velocity of the charge carriers. The current density is equal to current by area of cross section. Therefore, we can write it as Jx is equal to Ne Vx. And we can write it as Vx is equal to Jx by Ne. So there we have an expression. Now substituting this expression here, then what happens is Ey is equal to Hz Jx by Ne. We can rearrange, we can rewrite this expression Ey by Hz Jx is equal to 1 over Ne, and that is equal to RH, and this is called as Hall coefficient. So the Hall coefficient RH is 1 over the carrier concentration into the charge. If the Hall coefficient is a positive value, then the type of charge carriers are holes. If it is a negative value, then the type of charge carriers are electrons. Okay, so Hall coefficient is a very important parameter in the experiment, in the Hall effect experiment, to determine the type of charge carriers. Now we have an expression, we can rewrite this expression as Ey is equal to RH Hz into Jx. We get an expression for Hall field Ey is equal to the Hall coefficient into the magnetic field into Jx. We know that the mobility of the electrons mu is equal to unit drift velocity per applied field, and therefore Ey can be written as Ey. We have in the earlier expression we had Hz into Vx, so we can rewrite the expression as mu into Ex, is it not? So similarly we can write it as Ey is equal to Hz mu into Ex. So we can write it a Hall field in terms of the mobility of the charge carriers and the external field. So Ey, the ratio between Ey and Ex is equal to Hz into mu, and that is equal to the Hall angle, and this is called as Hall angle. So we have Hall coefficient RH, and Hall angle is the ratio between the Hall field in the y direction and the applied field in the x direction. So Hall angle. So we have two expressions, and Ey has two expressions. Ey is equal to Hz mu into Ex. Is it not? And another expression in terms of Hall coefficient, RH into Hz into Jx. So we can equate this expression, and Hz mu into Ex is equal to RH Hz into Jx. We can cancel Hz. So mu is equal to RH Jx by Ex. Ex by Jx is resistivity, and therefore 1 over resistivity is conductivity. So here RH Jx by Ex is nothing but 1 over resistivity, and this is conductivity. So this is the expression for Hall mobility of an extrinsic semiconductor. Hall mobility of an extrinsic semiconductor material. So we have found out the values of for an extrinsic semiconductor RH, Hall angle, and mobility of the external semiconductor, which is having the majority carriers as holes or electrons. For example, n-type semiconductor, it is a Hall coefficient value will be negative, so the majority carriers are electrons. If it is a p-type semiconductor, the Hall coefficient value is positive, then the majority carriers is holes. We can measure the mobility of the electrons or holes using the Hall mobility mu. So Hall angle is the ratio between the Ey and Ex, that is a Hall field and the applied electric field. So if what happens to the expression for Hall coefficient if it is an intrinsic semiconductor? Let us consider the case of an intrinsic semiconductor, that is undoped semiconductor. In case of an intrinsic semiconductor, the number of electrons are equal to the number of holes, that is equal to Ni. Number of electrons is equal to number of holes, that is equal to Ni, intrinsic. But the mobility of electrons are greater than the mobility of holes normally. So in intrinsic semiconductor, for like a silicon which is undoped, we have to find out the expression for RH. So in this case, the current density Iy in the current density along the Hall field direction Iy can be written as by the two terms, that is minus Ne. The negative sign indicates the direction of electrons flowing opposite to the current, conventional current. The charge into the velocity of electrons along the Hall field. And there is another term NH, that is N suffix H indicates the number of charge holes into the charge into VH. So mobility of electrons is given by V by Ey. And mobility of holes is given by VH by EY. So we can rewrite the expression VE is equal to mu E EYE. Mu VH is equal to mu H into EYE. So if we substitute the values of V, velocity of electrons in the Hall field direction, velocity of holes in the Hall field direction, in the current density values here, substituting VE and VH. If we do that, and that is equal to minus NE, the charge, into mu E EYE plus NH E mu H EYH. So this is the current density value along the Hall field direction. So we know that EY or EY Hall field direction is equal to Hz mu into Ex. We know that this expression already, and we can substitute the expression here. Iy is equal to minus n suffix e, charge of electrons, and we have mu e. Hz, instead of Ey, we can write it as Hz mu e into Ex plus NH E mu H Hz mu H into Ex. So we can write the expression as minus n suffix e, charge mu e square Hz Ex plus n suffix e n H e mu H square into Hz into Ex. So the common terms can be taken outside. Hz Ex, E into Hz Ex into NH mu H square minus Ne mu E square. This is Jy. This is Jy. So Hall field direction can be represented like the charge, the magnetic field, external applied field, NH mu H square minus Ne mu E square. Now Ey is equal to Jy, that is by sigma. So we have an expression for Ey is nothing but the current density by the conductivity, and where the conductivity is nothing but Ne mu. In case of intrinsic semiconductor, we have the conductivity can be represented as Ne E mu E plus NH E mu H. So we can rewrite the expression as for Ey, that is the field along the Hall field along the y direction. Ey is equal to E into Hz Ex NH mu H square minus Ne mu E square divided by E into NH mu H plus Ne mu E. So E can be cancelled. Once again, Ex is equal to Jx by sigma. So substituting the value here instead of Ex, we get an expression Haz Jx into NH mu H square minus Ne mu E square divided by E into NH mu H plus Ne mu E whole square. So this is an expression for Ey. So we know that Ey by Hz into Jx is equal to Hall coefficient, and that is equal to 1 over Ne, and that is equal to, we can rewrite this expression as we know that, already know that NH is equal to Ne, that is equal to Ni in case of intrinsic semiconductor. So what we can do is Ni can be taken outside. So we have a term mu H square minus mu E square divided by E into Ni square mu H plus mu E whole square. Ni cancels, so we can write it as 1 over Nie into, we can write as mu H minus mu E into mu H plus mu E. So mu H plus mu E and mu H plus mu E cancel. So we can write it here as mu H minus mu E divided by mu H plus mu E. So expression for an intrinsic semiconductor, Hall constant for intrinsic semiconductor is given by 1 over N intrinsic carrier concentration into the charge and the mobility of the holes and the electrons. So mu H minus mu E by mu H plus mu E. So this is the Hall constant for an intrinsic semiconductor. We have seen the Hall constant for an extrinsic semiconductor is given by 1 over Ne, that is equal to Ey by Hz into Jx. So we have seen the Hall effect is used to find out the type of charge carriers using the Hall constant for H, and number of charge carriers N, that is carrier concentration, mobility of the charge carriers, and also we can find out the, using the Hall effect measurements, we can find out the conductivity of the charge carriers. So in an experimental setup, for example, in an experimental setup we have the sample So let's consider this a sample, and supply is given. Measure the current, vary the current flow in the external field. We can apply using this setup, that is a battery, measuring the current and the rheostat, so adjusting the current flowing through the sample. Let us consider this is the thickness of the sample and this is the breadth of the sample. So we measure the Hall voltage using a VTVM. So we have an expression RH is equal to Ey by Hz into Jx. The Hall field Ey is equal nothing but Vh by d. Vh VH by D. Jx is nothing but current density is nothing but current divided current by area. So the area here is the cross-sectional area, that is because of the width and the thickness, D into T. So substituting the value here in Hall coefficient, we have RH is equal to VH by D divided by HZ I by D into T. We can rewrite the expression as VHT by HZ into Ix. So the value of Hall coefficient can be determined by the Hall voltage, thickness of the sample, applied magnetic field, and the current which we are measuring. So now we can rewrite the expression for Hall voltage as RH Hz into Ix by T. So this is the value of Hall voltage. So in an experiment, we apply an external field, magnetic field, we measure the current, the voltage, and Hall coefficient, VHT by Hz into Jx. So we can tabulate and we can find out the values and finally calculate the RH value. So this semiconductor material, this is an experimental setup for the semiconductor material. So what is the significance of Hall effect? Let us consider a device, for example a solar cell device. Let us consider a solar cell device where you have a P-type semiconductor and an N-type semiconductor. N-type semiconductor is called emitter or the buffer layer, and a transparent conducting oxide, TCO, that is the anti-deflection coating, transparent conducting oxide layer. So we have the P-type material, that is the absorber material. N-type material is the emitter layer, and TCO is the transparent conducting oxide. Transparent conducting oxide. So let us consider this is a solar cell of any material, for example silicon or copper indium diselenide or cadmium telluride, any type of P-type material. N-type material can be N-type silicon or N-type cadmium sulfide. Lot of materials are there. So this is a device. When the light falls on the material, a voltage will be created. Let us have this contact, and therefore a voltage will be created. So before fabricating a device, we have to understand the basic of the semiconductors here. Usually an observer layer should be having a carrier concentration of 10 power 17 to 10 power 18 per centimeter cube, observer layer. So by using the Hall effect measurements, we can characterize the number of charge carriers present in that particular material. For example, TCO requires 10 power, it's a degenerate semiconductor material, that is requires 10 power 21 per centimeter. Concentration of the carriers in the transparent conducting oxide should be in this range. So each and every semiconductor layers, p-type, n-type and TCO layers are having different carrier concentration. And the holes will be the majority carriers in the p-type and electrons will be the majority carriers in the p-type, n-type. So once the photon incident on the junction, the holes have to come to this particular region. That is, it has to, from the junction, it has to come to the contact. So how mobile is the holes? How mobile is the electron? If they are having a very good mobility, then that is very important for the charge separation. So if the charge separation is more, then the output voltage will be more. That is, VOC will be more. We have more output, that is open circuit voltage in the solar cells. Therefore, that will increase the efficiency of the solar cell. So we have to measure which type of charge carrier concentration, and before that we have to measure what is the type of charge carriers. So we have to say that this is a p-type and this is n-type. So for that we have to use the Hall coefficient, and this Hall coefficient will determine the type of charge carriers. That is, holes is here this is a p-type material and this is an n-type material, and again this is an electron rich transparent conducting oxide. So all those things can be measured using Hall coefficient. Then the type of charge, number of charge carriers, mobility of the charge carriers, and nowadays in the experiments, the Hall effect measurements are there. So we can also measure the electrical parameters like conductivity of these layers, and therefore all the significant electrical properties can be measured using the Hall effect. Such a very important measurements can be done using Hall effect. And this Hall effect was discovered by Hall in 1879. That is, he is Edwin Herbert Hall. He is an American physicist who discovered the Hall effect. So now let us consider a problem. Consider a semiconductor crystal of thickness 0.02 meter thick, 0.001 meter width, with a current of 0.002 ampere flowing along the length parallel to the long side and perpendicular to the current. The magnetic field perpendicular to the current, the magnetic field 0.5 Weber per meter square is applied. The Hall constant or Hall coefficient is given 3.84 into 10 power minus 4 meter cube per coulomb. Calculate the Hall voltage and also the carrier concentration. That is a problem given. So we have to find out the Hall voltage. As I indicated earlier, VH is equal to RH into current into the magnetic field. We can write it as B or H and the thickness. So RH value is given here as 3.84 into 10 power minus 4, that is written here, into the current value, which is 0.002 ampere, into the magnetic field 0.5 divided by the thickness 0.02, and we get a value of 19.2 microvolt. We can measure the Hall voltage. And the next thing is carrier concentration N. So RH, we have the relation RH is equal to 1 over NE, and therefore you can rewrite as N is equal to 1 over RHE. So we know the value of Hall constant, and also we know the value of charge 1.602 into 10 power minus 19. If you substitute the value, then we can find out the value of carrier concentration as 1.623 into 10 power 22 per centimeter cube. So the Hall effect measurements are very significant to understand the basic properties of the semiconductors, and from that we can, from understanding these properties, we can optimize the layers of the semiconductor. We can optimize the layers of the semiconductor, and in turn we can fabricate the device, a complete device. So thank you for active listening. Thank you very much.